hope that I'm able to impart at least a little bit of fun in this. So some of you haven't had our Physics 230 course. I'm going to start by giving us J.C. Maxwell. Our just brief jump into Physics 230 land, and then we won't use this, but the Maxwell equations. So I'm going to give you the integral form. So first, E dot dA is Q enclosed over epsilon naught. The kind of the symmetry here between P and B.
What's the value of E epsilon naught again? Pi divided by something?
Well, so K is 8.99 times 10 to the 9 Newton meter squared over Coulomb squared.
Okay.
You take epsilon naught and 1 over 4 pi epsilon naught is K.
Oh, okay.
I know I can say that.
Oh my god. Oh, okay, thank you.
So you can flip it. B dot dA, at least so far as we know, is 0. We've never seen any experimental contradiction of this. E dotted with ds minus dp dt, and B dotted with ds mu naught I plus mu naught epsilon naught dpe dt. So these are the equations which at the end of your Physics 230 class you probably saw can lead you to a traveling electromagnetic wave. And so this is kind of the period at the end of the sentence, at least for a while, that spoke to light being a wave. And so I'm going to spend the next several weeks talking to you as though light is a wave. And then I'm going to spend the latter 6 weeks or so of the semester, and I'm going to hedge on that a little. I'm going to show you that light behaves as both a wave and a particle. But at least for now, we're going to start from this wave assumption. So let's jump much further back to Galileo. Galileo asked a question that, well, he asked a lot of questions that I think have lasted through the years. But one of them was, how fast does light travel? And probably just experientially, you've noticed that it travels really fast, if not instantly, right? And that was something that Galileo and lots of people questioned. Is the speed really fast but finite, or is it infinite? And so Galileo attempted an answer at this. He and his assistant traveled to two nearby peaks, separated about 10 kilometers from one another. In my head, I always like to think that Galileo chose the peak next to his home, and his assistant took the far peak. Actually, I don't know, but that's my guess, if I had to guess. They had kind of this system worked out in advance where they had lanterns. I can't draw a lantern, so I'm going to draw a flashlight. Can't draw flashlights either, so I don't know, deal with it. But the rough structure here is it gets dark. One of them uncovers their lantern as a sign that they're ready to begin, and then they both cover their lanterns again. And so now Galileo uncovers his lantern. His assistant sees the light and responds by uncovering his lantern. And so the signal travels back to Galileo. What does Galileo observe? So ideally, right, the speed of light in this experiment would be equal to, well, 20 kilometers divided by delta t travel, the actual travel time, plus delta t reaction. Right, because the way this goes is first the lantern is uncovered, the light travels there, right? Travels half the total distance. The assistant has to react, so has to see it and then react by uncovering his lantern. Then the light has to travel back. Yeah?
Yeah.
And so we don't want this. This isn't part of the speed of light. Yeah? And so this needs to be subtracted out. So this is the total time. We want to subtract out the reaction time. Does that make sense? Does that work for you guys? Yes?
Yeah.
Okay. So, what did Galileo observe? Well, he observed that delta t travel plus delta t reaction minus delta t reaction was 0. He wasn't able to distinguish any difference between the total time and the reaction time. And so what he's able to take from this is that the speed of light is at least that that the time it takes light to travel 20 kilometers is small in comparison to the reaction time of his assistant. And so he, in some sense, could set a lower bound for the speed of light, but he wasn't able to set an upper bound. Does that work for you? Okay, so all Galileo could really get from this is that the speed of light was faster than he was capable of measuring with the tools he had. So he is at least tangentially related to our first decent measurement of the speed of light. And I'm using decent kind of qualitatively here. So, has anyone heard of the Galilean moons of Jupiter?
Yeah.
So Galileo used a telescope to look at the heavens. One of the things he saw was that Jupiter has moons. He could, we're into the 60-something moons of Jupiter now. But he could see the 4 big inner moons of Jupiter: Io, Europa, Ganymede, and Callisto. And the orbital period for Io is about 41 hours. 42 and a half. It really, loops around Jupiter in a hurry. Note that how long does it take Earth to orbit Sun?
24 hours.
A year.
65.
So
It's one rotation.
Go faster, bro.
So Earth can rotate on its axis about once every 24 hours, right? But the orbital period is significantly longer than that. In a little bit more time than it takes for Earth to spin around once, Io has completed an entire lap around Jupiter, right? That's
Just because it's a smaller radius, right?
It is. That is part of it, but it's also so radius is small. Jupiter's gravitational influence is pretty big, right?
Yeah.
How long does it take Moon to orbit Earth? A moon, right? One moon.
In days, how many days was that?
Whether you're talking synodic or sidereal, 27 and change, 28, 27.4, I think.
Months, approximately.
Yeah. Io is really moving, is the moral of the story, right? So Galileo and a bunch of other people thought that this would make a really good way of standardizing time measurements across the planet, across Earth, that you could use the eclipsing period of Jupiter to understand to get some relative time measurement across great distances, right? And so there was some research activity in trying to really understand the orbital mechanics of Io. But it had some unique features. So one is that when Jupiter and Earth were receding from one another, moving like the distance was increasing, the eclipsing period for Io was longer than if the two were actually getting closer together, Jupiter and Earth. And Romer had this kind of good insight that it couldn't be that, it wouldn't make sense that that difference in time was coming because of something that Io was doing, that it really had to be related to what was going on between Earth and Jupiter, right? That Io's eclipsing period doesn't care whether Earth is moving towards Jupiter or moving away from Jupiter, right? That's and so kind of I like this because it's a back of the envelope style calculation, but so we just said this. How long does it take Earth to complete an orbit?
365 days.
Simplify that for me. 1 year? Yeah. So for Jupiter, roundabouts, I'm really roughly sketching this at this point. It's about 12 years. So here's the sun, neglecting some other stuff, right? Here's the Earth. Not at all the scale. Here's Jupiter, right? So in the time that, by the way, about how long does it take for Earth to complete 90 degrees of its 360-ish degree lap? A few months, right? A quarter of a year. Roundabouts, pretending perfectly circular orbits. So Earth goes from here to here in a few months. Yeah?
Yeah.
How far does Jupiter go in that same time window? True. A little more quantitative.
A quarter over 12? I
1
don't know.
over 4?
So if this is 90 degrees, I like that. 90 degrees over 12? Is that? So I'm pretending like I'm doing this in my head. I'm not. It's in my notes. 7.5 degrees. Yay. So Romer guessed that the increase, like if you looked at just how much, like if you started counting here, you synced a clock. Io's orbiting once every 42.5 hours. That clock starts to lose time over the next few months. He argued that that was because it took light more time to travel that extra distance. And so that extra distance, give or take, is roughly one Earth orbit. One radius, one extra radius is what he argued. So
So to travel from one planet to the other one, is that what you mean?
No, I mean, this distance is our Earth, or our orbit Earth.
Uh-huh.
So I can imagine a triangle here. And now I've got use that for Earth. So Jupiter, Earth. That we've gone from our Jupiter minus our Earth to something that is, well, this angle is so small that this hypotenuse and this, right? So originally what you had is this was RJ, this was our Earth, yay? Then we're going to go to RJ, our Earth, but our Earth is so small compared to RJ. This angle is so small, the hypotenuse is basically the same as RJ, right? It's just barely bigger. And so what is delta R then?
Close to zero, right? Is it there equal?
Delta R is just our Earth, right? We've gone from this distance, RJ minus RE, to just RJ. Yay? Do you guys see that? So originally, let me do this in a different color. The distance, again, this isn't to scale, which is partly why I think I've made this. So this is RJ minus RE. Yeah? But the new distance is this. Yeah? That's this hypotenuse. But our Earth is so small compared to our Jupiter that the hypotenuse is basically the same. You guys remember that for theta much less than 1 radian? Sine of theta is approximately what?
Theta.
Theta.
Cos of theta is approximately what?
Theta.
This is where our issue comes in. It's basically 1. So remember, this is our hypotenuse, right? So if this is theta, we can say that cosine theta is equal to
1.
RJ over the hypotenuse, right? But if this is roughly equal to 1, what does that say about about the hypotenuse?
Because
It's roughly equal to RJ, right? And so the distance before was RJ minus RE, but the new distance is what? It's basically RJ, yeah? Yeah? And so what's the difference between these two?
Wait,
Or
sine of theta should be 0, not theta.
For small angles, what is theta? It's very close to 0.
Wait, you are making 0 with theta. Sine theta. Oh.
Sine theta is approximately theta,
Oh, okay, good. Because
but for small angles, to Chris's point,
oh, okay.
that means theta is very nearly 0, right?
Oh, okay. Good.
Radians. All right. If the earlier distance was rj minus re and the new distance is rj, what's the difference?
RE.
Re, right? Which, again, re compared to rj is really tiny, but it's not that tiny. It's 1.49 times 10 to the 11 meters. So, so this gives kind of a rough way of measuring the speed of light, because if you get a maximum delay of about 600 seconds, which isn't nothing, right? On the order of 10 minutes.
10 minutes.
Yeah, so if you started setting your clock here and expected to see an orbital eclipse start or end every 42.5 hours, and then you let that play, by the time you got to here, you would see that the start or stop time is delayed by about 10 minutes, right? And that's, but this affords a chance, because Romer is going to tell us that that delay is coming entirely because the extra travel distance. That extra travel distance is about one Earth orbit, why do I keep saying that? The radius of one Earth orbit, which is, again, about 1.49 times 10 to the 11 meters. Due to some problems with, one, the timing wasn't really 600 seconds. Two, the size of the orbits wasn't that well known. And so there were a couple of issues here, but Huygens and Romer guesstimated that the minimum speed for the speed of light is about 2.3 times 10 to the 8 meters per second. Anyone know what the rough value of the accepted speed of light is? Three. 3 times 10 to the 8. So, what is that, like 70-ish%? A little more than that, maybe. Good. Not perfect by any means, but he's able to show that it's not infinite, right? If it was infinite, what would this delay have turned into? Zero, right? The fact that he saw a delay implies that there is a speed of light, right, that isn't infinite. Does that work?
Pretty cool explanation. I like it.
So yeah, I love stuff that you can do with, that you don't need super fancy equipment for. You can. Here's a date idea for you guys. You live in California. You can measure the average radius of the Earth by going to the Cliff House in San Francisco and watching the sunset. You have to know how high up you are. Like, you need to know how high above the beach you are. But and there's a little bit of a problem here, and that the Earth isn't really a perfect sphere; it's an oblate sphere. And so you're kind of mushing things a little bit. But you could also get there just by looking at the shadow cast by a stick, if you happen to, live at a lucky place on the Earth, right? I like experiments you can do that don't require $1 million equipment. Okay. slightly better version of, well, different version, but slightly different attempt by PHYS231, 1849. Pretty sure that he was French. Even if he isn't, my grandmother will insist that PHYS231 was French. So, that looks like the coronavirus, but it's intended to be like a toothed gear. You know what I'm talking about? Like a sprocket? Yeah, okay. So, in PHYS231's experiment, he knows the locations of these very, very, very well. It's like micrometer level well. He's got it on another geared drive. So he knows the distance between this wheel and this mirror very, very well. And he also has the ability to control the speed of rotation of that geared wheel very, very, very well. And so then he just takes a light and he shines it through. And he varies the speed of rotation until the light can go through but can't make it to the mirror and come back. Right? And so he's going to find the rotational speed, right, at which the light passes through, so it makes it through the space between one pair of teeth, and then it can't make it through again. You could even do this in a simpler fashion by having only two gaps, right? So that light comes through one side, you even know which gap it made it through if there's only two, right? It reflects off the mirror. If you get the time right, you can find how long it takes for one pulse to come back. Does that work? Mm-hmm. And so then you have a good knowledge of distance and a good knowledge of travel time, because you know how fast you're turning this wheel. This version of the experiment, PHYS231 is able to get to a speed of light of 3.1 times 10 to the 8 meters per second. It's not right either, but within experimental uncertainty bounds, it carries the right value. Later versions, more precise versions, get us up to 2.9979 times 10 to the 8 meters per second, which is very, very close to the now adopted value. Yay enough.
So that's
Wake up.
the 2.9979 times 10 to the 8 is the accepted value, right?
Sort of. It was very close. To the value that you get from this. So, by the way, you can derive the speed of light from these four equations. It's really neat. But, so, yes, definitely within error, this matches the value for Maxwell. We've since actually just defined the speed of light. And so So now it carries more decimal places than, but for our purposes, we'll use 3 times 10 to the 8. If we're ever doing something that requires that much precision, we'll go to 2.998. But for the most part, 3.0 times 10 to the 8 meters per second. 186,000 miles per second. I want to point that out, right? 186,000 miles per second. That's not miles per hour. Miles per second, right? So
Wow, so
That's
fast.
how many times going around the planet?
several. But it's you could travel to the moon if you were a light pulse in just barely over a second. So,
It's never gonna happen with humans.
no.
Beam me up, Scotty.
So we were talking about the sun on average is about 1.49 times 10 to the 11 meters away from Earth. Well, at this speed, it takes light about 8 1/3 minutes to reach us from the sun. So
Oh my god.
that's our star, right? We don't do this anymore, but well, maybe I'm speaking too broadly. I don't do this. Anyone ever borrow anything from their neighbors, like sugar or?
No.
Yeah.
Yeah.
I don't know who does that.
I did that.
I know, like where I live now, I actually know the names of the neighbor to my left, the neighbor to my right, but on my court, the neighbor across the court from me, I don't know her name.
I don't
So
know.
I know her dog's name. So but,
That's what counts.
I'm just saying that, like, yeah. In days gone by, maybe everyone knew their neighbors, or maybe that's just one of those things that we tell our children.
Well, I lived in the East Coast for a while, and people still come over and introduce themselves when you move. It's just a West Coast thing, I think.
Yeah, I want to moat. So, or lasers. But our next nearest neighbor, like sun is our star, right? Anyone know? I know one of you does. Who our next nearest neighbor star is? It's even in the name. Proxima Centauri.
Oh.
So we named it because it's in our proximity, right? That is the next closest star to us, other than our sun, the one that we orbit, right? Anyone know how long it takes for light to reach us from Proxima Centauri? It's our neighbor. It's who we go to borrow sugar from. 4.2 years of traveling 186,000 miles
Jesus
every
Christ.
second of every minute of every hour of every day of every year for 4.2 years. So
It is crazy.
the galaxy is giant. The universe is even bigger, right? So we are tiny. But the speed of light is very fast.
Isn't that why they're trying to find a warp drive instead of a speed of light drive?
Because things are far away.
Yeah.
Yeah, I mean, yes. If you ever wanted to live, to make the trip to somewhere far, far away, like Proxima Centauri even, let alone one of the stars further, we couldn't. Not without cheating, and so that's the goal of attempting to kind of shorten the distance artificially, right? The other way to view it is, long-range space exploration, if we ever choose to do something like that. It's a generational thing, right? You don't, the people who leave aren't going to be the people who arrive. Okay, so with that in our back pocket, speed of light, really, really fast, about 3 times 10 to the 8 meters per second. There is kind of this long-running argument throughout history: is light a particle? Is light a wave? Many people have argued for both over the years. Some great names in physics have argued on both sides. The idea of light as a particle even creeps into kind of pop culture, right? Have you ever heard the expression giving someone the evil eye? Even if you haven't heard it, I know you guys are aware of it because I see the way you look at me. But this dates back to a time when that was a common notion, that the way you saw was your eye emitted things. I think they're called corpuscles, that would travel from your eye off the thing you were looking at and then back to you, right? And so this idea that if you thought just some really unkind thoughts, that those would travel with the particles to the thing you were looking at. But we've got, as we'll see, we'll do this experiment. The Young's double slit experiment shows interference. In your physics 130 days, you saw that you could add or subtract waves by making them coincide, right?
It's actually on the homework too.
It's also in your homework, but physics 130. Things that I know you guys have actually done. Homework, I mean, come on.
Heartbroken.
Again, empty, not broken.
Liquid.
The Young's double slit experiment shows that if you pass light through a pair of slits and then make it land on an observing screen, you'll actually get an interference pattern. And that's pretty solid evidence that light has some wave properties. It's also such that if you want to derive the speed of light from Maxwell's equations, you have to assume that it's acting as a wave. So that really seemed to settle things in the mid to late 1800s. It's pretty well accepted. Light is a wave. But then we're going to get to the early 1900s. I know it seems like ancient history to you, but it's not. Take it from someone who's old. That's not ancient history. The early 1900s, we're going to have some experiments that the only way we're going to be able to explain the results is if light also has some particle properties. And so optics, I'm going to teach from a very, very classical standpoint. And so we are going to just go whole hog, pretend that it is definitely, most certainly a wave. And then I'm going to kind of hedge on that again in a few weeks when we start talking about 20th century physics. So with that, so geometric optics, we're going to assume that light travels in straight lines. It's only going to deviate from that